Well, in my previous lecture, we have seen the photoelectric equation given by Einstein, which is given by h nu equals to the energy of the incident light is equals to the work function phi plus the kinetic energy of the ejected electron, the Ke of the ejected electron. Of course, this is the maximum kinetic energy value. Then the de Broglie's wavelength lambda is given by h by p, where p is the momentum, mass into velocity. So these are the two equations that we have seen in the last two lectures. Now in this lecture, we'll do some exercises based on these two equations. Let's take the first one. First question is very easy, the basic question. Calculate the energy of a photon of blue light whose wavelength is given as lambda is 450 nanometers, 450 nanometers in air. So we are supposed to find the energy of the photon whose wavelength is given as 450 nanometers. So how do we go? So we know that energy is equals to h nu, Planck's constant, into frequency of light. Then what is the connection between frequency of light and the wavelength of light? We know that the speed of light c is given by the product of wavelength and frequency, nu lambda. So I can substitute c by lambda here in the place of frequency. Why? C equals to nu lambda, then nu becomes c by lambda, and we know the value of c, we know the value of c, we know the value of h. What is c? C is 3 into 10 power 8 meter per second. Planck's constant is 6.63 into 10 power minus 34 joules second. So these two values we know it. So you can replace frequency by c by lambda. Put the value of lambda, then put the value of c, h, substitute these values and simplify it, we will get the value for energy. 6.63 into 10 power minus 34 into 3 into 10 power 8 divided by lambda is 450 nanometers. What is 1 nanometer equals to? 10 power minus 9 meters. So simplify this, we will get the value for energy, as simple as that. So what is this? So first take the 10 power of 10 terms, 10 power minus 34, 10 power 8, 10 power minus 9. If you take this minus 9, it becomes plus 9, 9 8 17, then 17 minus 34 becomes 10 power minus 17. Then 3 into, or we can do this, 3 ones, 3150. Then 6.63 by 150, or else I can remove this 0 also, I can make it 10 power minus 18 here, because this 150 can be written as 15 into 10. So I can make it 10 power minus 18. Now 6.63 divided by 15, so it is roughly around 0.44 into 10 power minus 18 joules. Or you can write it as 4.4 into 10 power minus 19 joules. So this is how we calculate the energy of a given photon when wavelength is given. If frequency is given, you can directly put the value of frequency here, multiply with Planck's constant. So value is 4.4 into 10 power minus 19 joules. If they ask the value of energy in terms of electron volts instead of joules, what is the conversion needed? We know that 1 electron volt is equals to 1.6 into 10 power minus 19 joules. So suppose in the question if they ask the value of energy in terms of electron volts, then how do we convert this? This becomes 4.4 into 10 power minus 19 divided by 1.6 into 10 power minus 19 electron volt. So minus 19, 10 power minus 19, 10 power minus 19 get cancelled up. 4.4 by 1.6 is almost 2.8 electron volts, roughly 2.8 electron volts. We'll get it. So this is how we calculate the value of energy. This is the basic question: how to find the energy when lambda when lambda is given or when frequency is given. The simple formula for finding energy energy is h nu, where nu can be substituted as c by lambda. Put the value of lambda, value of c, value of h. Simplify it. Let's go to the next one. Next question. The photoelectric work function for sodium is given as 2.7 electron volts. If light of frequency flight of frequency 9 into 10 power 14 hertz falls on sodium, find first question the stopping potential, then B, the kinetic energy of the most energetic electrons ejected, and C, the speed of those electrons. The speed of those electrons. So given the work function for sodium is 2.7 electron volts, light of frequency 9.9 into 10 power 14 hertz is falling on the sodium. Now we are supposed to find the stopping potential, the kinetic energy of the most energetic electrons ejected, then the speed of those electrons. How do we proceed? As I said, a single equation. The photoelectric equation is h nu is 5 plus Ke max. We know this equation. Now first we are supposed to find the stopping potential. How do you find the stopping potential from this equation? We have seen a relation in my previous lecture. The Ke max is given by EV0, where V0 is the stopping potential. This is nothing but half mv square, mv max square. So if you put EV0 here, the other values we know, h we know, frequency is given, phi is given, then E we know. So put the values, simplify it, you will get V0. Then put the value of V0 in this equation, you will get the kinetic energy, and then once you get the kinetic energy, you can find velocity of the electron from this equation. As simple as that. So first let's go for V0, find V0. What I do is I'll put EV0 here instead of Ke max. Then what it becomes, equation becomes EV0 equals to h nu minus 5. You can write h nu minus 5. Take this 5 on the other side, E V naught is h nu minus phi. Now what is V naught? Applies V naught is h nu minus phi divided by E. Now just put the values. Therefore V naught, the value of h is 6.63 into 10 power minus 34 into frequency 9 into 10 power 14 divided by, minus, what is phi? 2.7. 2.7. It is given in electron volts. We have to convert that into joules. Why? Because the Planck's constant, the unit for Planck's constant is joule second. We are taking energy in terms of joules. So everywhere we have to use the same units. We cannot directly subtract joules, electron volts from joules or joules from electron volts like that. The energy unit should be same everywhere. So since we have joules here, we have to convert this electron volts into joules always. 2.7 into 1.6 into 10 power minus 19 joules. Let's leave this. So this is the conversion. 1 electron volt is 1.6 into 10 power minus 19 joules. Divided by E. What is the charge? Charge of electron? 1.6 into 10 power minus 19 coulombs. Now let's simplify this. Simplify this, we'll get the answer for stopping potential. How do we simplify this? So first take this, simplify this. Powers of 10, 10 power 14, 10 power minus 34 is 10 power minus 20. Then 9 into 6.63. 59.67 into 10 power minus 20. So 9 into 6.63 is 59.67 and 10 power 14, 10 power minus 34 becomes 10 power minus 20 minus, what is 2.7 into 1.6? It's 4.32. So 4.32 into 10 power minus 19 divided by 1.6 into 10 power minus 19. Since we have 10 power minus 19 here and here, let's make this also 10 power minus 19 so that we can easily cancel up these terms. Then what happens? This point will shift here. So 5.967 minus 4.32. How much is that? So 5.967 minus 4.32, it's 7, 4, 6, 1. 1.647 into 10 power minus 19 divided by 1.6 into 10 power minus 19. So this is your V naught. So after simplifying this, we will get roughly around 1. Because 1.6, 1.6, it will be around almost approximately 1.03 volts. So this is the stopping potential. This is the stopping potential. This is how we find. As simple as that. Just take the photoelectric equation, substitute the values. Now once you get the stopping potential, you can find the kinetic energy of the most energetic electrons. How do you find that? As I mentioned, Ke max is EV naught. So E into V naught is known, 1.03 volts. So therefore we can simply write it as 1.03 electron volts. So this is the kinetic energy, maximum kinetic energy possessed by the electron. So Ke max is 1.03 electron volts. That's it. Now part C, the speed of the electron. We can find that. Put the value, Ke is half mv square. From this equation, you can find the speed of the electron using this. So I'll write this as half mv max square equals to 1.03 electron volt This implies what? This implies Vmax. Vmax is 2 into 1.03 electron volt divided by m, the mass of the electron, under root. We know the mass of the electron. This electron volt, again we have to convert this into joules. So I'll write it 1.6 into 10 power minus 19 joules. And what is the mass of the electron? 9.1 into 10 power minus 31 kg. Now we'll simplify this. Therefore, Vmax is, so this 1.03 into 1.6, I can get it from here. It is just 1.647. So I'll write it as 2 into 1.65 around roughly. Because 1.03 into 1.6, I know it is 1.647. So 1.65 divided by 9.1 into 10 power minus 31. Of course, 10 power minus 19 is there. So what I do, this 10 power minus 31, if I take it in the numerator, it becomes plus 31. Then 31 minus 19, we'll get 12. Now what is left? This equals to 2 into 1.65, 3.3. 3.3 divided by 9.1. Let's take it roughly around 9. Easy to cancel. Under root. If you take this 10 power 12, outside the root we'll get 10 power 6. Now how much is this? 3.3 by 9 is roughly 3.36 into 10 power 6. So root of 0.36 is 0.6. 0.6 into 10 power 6 meter per second. So this is the velocity, the speed of the most energetic electrons. 0.6 into 10 power 6 meter per second. Or else we can write it as 6 into 10 power 5. 6 into 10 power 5 meter per second. So this is how we calculate the stopping potential, the kinetic energy, and the speed of the electrons using the simple photoelectric equation. Once we understand the photoelectric equations, once we understand the terms in that, then everything is easy, as simple as this. Let's go to the next one. Next question. Ultraviolet light of wavelength (2000 angstroms) causes photo emission from a surface the stopping potential is 2 volts. Then find the work function, then B, find the maximum speed of the photoelectron, This work function you have to find it in electron volts. Photoelectron. So light wavelength, again we know wavelength is given So let's sort it out what all are given first. Lambda is 2000 angstroms, or I can write it as 2000 into 10 power minus 10 meters, because 1 angstrom is 10 power minus 10 meter. And stopping potential, we know what is that? V naught, it's 2 volts. And first one, we have to find the work function. Again, write the photoelectric equation. H nu equals to phi plus Ke max. In this Ke max, you can write it as EV naught, because we know that Ke max is EV naught, because V naught is given. So we are supposed to find phi, therefore phi equals to H nu minus EV naught. But nu is given? No. Lambda is given. So what I can write? This I can write it as Hc by lambda minus EV. So before simplifying this, we can simply put the values of Planck's constant, speed of light, lambda, E, charge of electron, V naught. We can do that. But instead of doing like this, we have a simple procedure of doing this. We should remember the value of Hc by E. If you remember the value of Hc by E directly, then our calculations will become little simpler. So what is the value of Hc by E? If I put Planck's constant, multiply with speed of light, divide by charge of electron, its value is around approximately 12,400 volt meter. 12,400 into 10 power minus 10, sorry, into 10 power minus 10 volt meter. If you remember this value, if you know this value, so instead of putting the value of Planck's constant and speed of light every time in the problem, we can simply use that value, so that our calculations become easy. I'll show how this works. Now since Hc by E, we know this, so what I do is divide E. We have to find the work function, so divide E on both the sides, on LHS and RHS. What it becomes? Phi by E is Hc by E lambda minus, it becomes V naught. Now we know this Hc by E, this value we know, lambda we know, so our calculation becomes easy. Otherwise we have to find the product of this Planck's constant and speed of light, then divide by the wavelength. It will be a little hectic. So this is the easy way to do it. We have to remember this simple formula. So now what I do is Hc by E equals to 12,400 into 10 power minus 10 volt meter divided by lambda is 2000 angstrom, so 2000 into 10 power minus 10 meters. So this quantity is volts and this quantity is also volts, so we can dimensionally these two are correct. So this quantity is in volts, this quantity is also in volts. We can subtract volt and volts. So minus, what is V naught? It's 2 volts. 2. Now calculations become easy. This equals to, what I do, this cancel, so it becomes 6.2 minus 2. We get 4.2 electron volts. Not electron volts, sorry, this is volt, right? This is just volt. 4.2 volts. Phi by E is 4.2 volts. Then we have to find the work function, not phi by E, work function by E, not this. So simply we take this E on the other side. What we get? Therefore, phi equals to, if I take this E to the right hand side, it becomes 4.2 electron volts, because phi is the energy. We always have to remember that phi is the work function, which is energy. So its units are electron volts or joules. Therefore phi is 4.2 electron volts. So our calculations have become easy when you are using the value of Hc by E. Then second, find the maximum speed of the photoelectron. Again, just like your previous method, we know this phi is 4.2 electron volts. So we have phi equals to 4.2 electron volts. Now for finding the maximum speed of the photoelectron, what is the Ke max? First, let's say Ke max is EV naught. We actually don't require this work function also. Okay, leave it. So EV naught, V naught is there, 2. So 2 electron volts. Ke max is 2 electron volts. Then what else? We have to find the speed, right? Find the maximum speed of photoelectrons. So half mv square, mv max square is 2 electron volts. Therefore V max, just like the previous sum, V max is 2 into electron volts to joules, 1.6 into 10 power minus 19 divided by, oh, one more 2 is there. This half, it also becomes, it multiplies here. 2 into this divided by mass. Mass is how much? Mass of the electron? 9.1 into 10 power minus 31. Simplify this, we will get the value for speed of the electron. How do you do this? So this is 4 into 1.6 is 6.4. So what I do is this 31, it becomes plus 31 in the numerator. 31 minus 19 is 10 power 12. So 10 power 12. What this is? 2 into 1.6, sorry, 2 into 2, 4 into 1.6 is 6.4 divided by 9.1. Implies V max, again write it as 64 divided by 91 into under root into 10 power 6. I am taking this power of 10 outside the square root, so it becomes 10 power 6. So this value, root 64 is 8 divided by root 91. Root 91 is roughly 9.5, we can say, approximately 9.5. So 8 divided by 9.5 into 10 power 6 meter per second. You simplify this, you will get the value, exact value. So this is how we do. The idea is, when you are given the wavelength or work for, the stopping potential, the basic equation is the photoelectric equation. If you understand that equation, if you know the terms related to that, what is stopping potential, what is work function, if you understand that thoroughly, then all the problems based on this is very easy to solve. Just we understand the things, what all are given in the sums, and what are we supposed to find it out. Just using the same equation, we can derive the other parts. Okay, we'll do the remaining exercise in the upcoming lectures.